All right. Welcome, everybody. We're going to jump into our final major topic we will cover this year before the exam. As a reminder, we will wrap up with and cover the other topics that are listed in the course and exam description after the exam. But given the changes, we're going to conclude with a couple days talking about Taylor series. So you already watched a video and took notes. I really do hope you took notes because it'll help explain and fill some of the holes in what I'm going to talk about. But we've kind of gotten to that point where you've probably been asking, okay, so why are we learning this series stuff right now at the end of calculus? Starting today, we'll start seeing why, and we'll start sort of revealing and talking about some of the important sort of calculus-related ideas that are roped up in this idea of series. Let's start with something from actually earlier in this unit, which you might be familiar with. Recall that this is what we call a geometric series, a times some r value to the n. If that r value, that absolute value of r was less than 1, so between -1 and 1 not inclusive. So if this r was like half or negative half or something like that, then this geometric series converges to this sum right here, a over 1 minus r. And let's say for the sake of argument that a value is 1. And let's, instead of r, let's call it x, because we're often used to dealing with x as sort of variable placeholders. Then we could say this, that this geometric series here converges to a is 1 over 1 minus x if the absolute value of x is less than 1. So that x value there is somewhere between -1 and 1, non-inclusive. All right. Well, we could understand this series, and we call this kind of series a power series. Let me actually switch to a thinner pen here. We could understand this power series. That's what we call a power series, okay? We could understand this power series that's written out there as representing the function this, all right? So this power series then, this series is equal to 1 over 1 minus x if the absolute value of x is less than 1. So this series actually represents this function if, and that's important, if the absolute value of x is less than 1. So this series approximates is this function for specific values of x. Okay, interesting. Hold on to that thought. But we need to remember that sort of special condition. We need to remember that any value where x is not 0, where x is not 1, will work for this function. But only the values, absolute value of x, that should be absolute value of x is less than 1, only those values will actually make this power series converge. Okay, digest that for a second. For this function, yes, any value x is not 1 will work. But if we're talking about this function and this series being the same, well, only when the absolute value of x is less than 1 will this power series converge and be equal to that function. So we kind of have a limited space here that makes this power series equal this function. That condition has to be present for this equation to be true. What that means is, going back to something we've already talked about, is that the radius of convergence of this function, the radius of convergence, the radius of convergence of this function is r equals 1. All right, and the interval of convergence, is the absolute value of x is less than 1. Now, we're not going to talk a whole ton about these two things today, but this is important, that this power series equals 1 over 1 minus x only for absolute value of x is less than 1. That's the interval of convergence. So the radius, how wide is sort of that space on the each side of x equals 0? It's 1, plus or minus 1 from x equals 0. This becomes true. Now, let's talk a little bit more about power series, okay? power series look like this. The sum from 0 to infinity of c sub n, so that's what we can call coefficient n x to the n, which is, well, if n is 0, so that would start off with coefficient 0 plus coefficient 1, x to the 1, plus coefficient 2, x to the 2, and so on. We call this a power series. And this power series, we say, so this is a power series. And it is a power series that is centered, ooh, there should be an R in there. Power, oh, I had the R. Power series centered at a value here of x equals 0. That's technically what we just had above. All right, power series centered at x equals 0. But we could also actually shift what that center spot is where we're making our series. We could move it back and forth using kind of our normal transformations. So actually, generally speaking, we'll think of these power series like this. C sub n of x minus a to the n, which is c sub 0, because n to the 0 would make that 1. Coefficient 1, x times x minus a to the first, coefficient 2 times x minus a to the 2, and so on. This is a power series centered at a, which is sort of our general formula. This one would be centered when a is 0, so we basically lose all of the a things. All right. Now, this may seem really trivial, this idea of power series, or the fact that that series above, the series of x to the n equals 1 over 1 minus x. But this is actually like incredibly important and useful mathematically. Because essentially what we're saying is that a function, a slightly complicated function like this, can actually be represented, at least to some extent, by a very, very simple infinite polynomial. For example, 1 over 1 minus x would be equal to, if you actually, if you actually went through the process of doing this series out here, if you actually went through this series process, that means 1 over 1 minus x is going to be equal to 1. So that's x to the 0 plus x to the 1 plus x to the 2 plus x to the 3, and so on and so forth. If we're in that interval of x values we are interested in, and we have seen so far for at least this one, that is the absolute value of x has to be less than 1. But that's still kind of radical, that this idea that a kind of complex function can actually just be represented by a series of power things. Essentially, it's an infinite polynomial. And like, digest that for a second, because this has a lot of important implications, right? Because as we've seen in calculus, functions and things like this are fairly complex to deal with in different ways. But polynomials are super easy. All they deal with is addition and multiplication when we take derivatives and integrals and things like that. And if you're thinking ahead in terms of computers, computers deal with addition and multiplication really easily too. So being able to equate complex equations to these kind of infinite polynomials is really, really powerful. Okay. All right. Let's play around with this idea for a little bit before we dive into actually what Taylor series are, okay? Let's find a power series. Let's find a power series representation for the following function and determine its interval of convergence, okay? Let's do that first. Okay. Gotta make sure I have my notes and stuff out. Okay. So let's see. 1 over 1 plus x. 1 over 1 plus x. Well, if I'm thinking about this, this is a whole lot like f of x. Well, I could rewrite this 1 over 1 minus negative x, right? And why might I do that? Well, I know what this one looks like. I know what 1 over 1 minus x looks like, right? I know that that would be equal to 1 plus x squared plus, oh, that shouldn't be x squared. 1 plus x plus x squared plus, and so on and so forth, x to the n, right? Well, look, I just have a negative in here. So really, what could I do? I could think about it this way. This is going to be really equal to, this is kind of like my new x value here. Instead of x, I'm going to have negative x. So really, what do I have? I have like negative x to the 0, because that's what that 1 was. That was x to the 0. In this case, it'd be negative x to the 0 plus negative x to the 1 plus negative x squared, and so on and so forth, right? So this, if I think about this, okay, this is going to be equal to this negative. This negative sign is going to be kind of interesting for me. If I think about this sum down here, I'd have, let's see, negative x to the 0, that's still 1. Negative x to the first power, so that'd be minus x, plus negative x squared, so that's going to be plus x squared, right? We can probably imagine that the next one will be minus x cubed, and so on and so forth. So if we want to write this out in sort of summation notation, this is going to be the sum from n equals 0 to infinity of, okay, n equals 0 to infinity of, it's alternating, so I'm going to need a negative 1, and I need to start positive, so this is going to be negative 1 to the 0, times the quantity x to the n. Oh, I made a mistake there. Not a negative 1 to the 0. It should be negative 1 to the n, right? N is starting at 0. Negative 1 to the n times the quantity x to the n. And we could test this, just make sure it matches. When n is 0, that'd be negative 1 to the 0, so that's 1 times x to the 0, that's 1, so I start off with 1. Then when n is 1, I'd have negative 1 times x to the first power. Boom. There we go. And this I should have written out as continuing, right? Okay. So here is my representation, my power series representation then of this original function. All right. And when we think about the interval of convergence here, if we're looking at the interval of convergence, it's still going to end up having the same interval of convergence. When we think about it, right, this here, we're using it x to the n, is still going to have, as its interval of convergence, it's still going to need to be the interval, we're going to do it in interval notation, negative 1 to 1, right? So that this term here gets smaller and smaller as it multiplies. Okay? All right. Here's what I'd like you to try. I would like you now to, if you could, practice for me this next practice problem. Pause the video, practice this next practice problem, and then come back and check to see if you got it right. All right, go ahead and do that. All right, so let's take a look here. We have a new kind of, or we have a new function that we want to find a power series representation for. Ooh, let me go ahead and get my thing. I'll scroll down a little bit there and clear out my other one. All right. Okay. So we're trying to find a power series representation of 1 over 1 plus x cubed, right? Okay. So let's see. We want to do some rearranging here to make it look like something familiar, so we can do that. We can come over here and say, okay, well, this is really going to be the same thing as, let's say, equals 1 over 1 minus, right? 1 minus negative x cubed. Because we want to try to compare it, if possible, to that thing we already know, which we said was 1 over 1 minus x, because we know how that looks now. We know that that looks like 1 plus x to the first power plus x squared. I always want to jump a power there. 1 plus x squared plus x cubed. We know what that looks like, right? Okay. So I rewrote this to try to make it look like something close to this down here, 1 over 1 minus something. All right, let me fill in what I know then. Okay, what I'm going to have here, this is kind of like my x thing down here, negative x cubed. So I'm going to put this as negative x cubed to the 0, because that's how I get this 1. That's really x to the 0, plus negative x cubed to the first power plus negative x cubed to the second power plus, and so on, right? So what does this give us if we think about the numbers here? Negative x cubed to the first power, that's 1, plus negative x cubed to the first power, so that's going to be minus x cubed. Negative x cubed to the second power, that's going to square that, make it positive, so plus x to the sixth, and so on and so forth, right? So what is our sum going to look like here? We can already start seeing some pattern. It's going to be the sum from 1 to infinity of, let's see, it is alternating, so we're going to need a negative sign in there still, right? We're going to need a negative sign in there. So I'm going to do negative 1 to the n. Oop, let's actually start this. Why did I put 1? We want to try to start them at 0 since we're based off of the function we already were looking at earlier. Sorry about that. N equals 0. There we go. Negative 1 to the n power. Negative 1 to the 0 give us 1. That's what we want. But then how do we take care of the rest of this stuff? So it's going, looks like 3, 6. The next one would be 9. So we're going to have a negative. We already took care of the negative sign, so it's going to be x to the, well, we had a cubed, right? A cubed there. And then we're taking that cubed and we're multiplying it by our n, right? So let's just say x to the 3n. How about that? Does that work? Negative 1 to the n, x to the 3n. If I plug in 0, I get negative 1 to the 0 times x to the 0. So that gives us 1. Get now n equals 1, negative 1 to the 1 times x to the 3. There we go. Great. So that would be my power series representation then. And if I think for a second here, all right, so what's this got to be? This is going to converge so long as whatever this absolute value of x cubed is less than 1. Hey, so what does that mean? That means the absolute value of x has to be less than 1. So I still have my same interval of convergence here, negative 1 to 1. All right? So it's still the same as the original power series. Because this had to be, this whatever this quantity is has to be less than 1. The absolute value of it, sorry, has to be less than 1. Interesting. Okay. So let's take a look at another example and keep exploring this leading up to our idea of Taylor series. Okay. So let's say that we're given this fact, the one we've already been dealing with on the interval negative 1 to 1. We know that works there, right? We want to find a power series to represent, this looks slightly more complex now, right? We have 1 over 1 minus x squared. Now, I'm going to speed things up a little bit just because I've set this problem up to show something in particular. But here's what we got to recognize, okay? If I know this, I know for a fact that 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x to the fourth plus, and so on and so forth, right? I know all that, which ends up basically being x to the n plus, etc. If I know that, basically, how do I get to this? Now, if I think for a second, kind of off to the side, and I remember my good calculus, I know 1 over 1 minus x is really 1 minus x to the negative 1. If I take the derivative of this, all right, so I'm going to take the derivative of that, and take the derivative of 1 minus x to the negative 1. I'm going to get, if I bring down the negative sign, right, bring down the negative sign, I'm going to get negative 1 minus x to the negative 2, because I subtract that power, times the derivative of the inside. The derivative of the inside is negative 1, so that's going to make it plus. Hey, what is this equal to? That's equal to 1 over 1 minus x quantity squared. Hey, that's what I'm looking for up here. Interesting. So, in theory, if I take the derivative of this, I'm going to get 1 over 1 minus x quantity squared. So if we take that derivative, I took the derivative of everything on the left side. I should be able to take the derivative of everything on the right-hand side, and it should be equal. In fact, that's how this works. So I'm going to do what's called term-by-term differentiation. The derivative of 1 is 0. We can write that down if we want to, but I'm not. The derivative of x is 1, plus the derivative of x squared is 2x, plus the derivative of x cubed is 3x squared, plus 4x cubed, plus, and so on and so forth, until I get to nx to the n minus 1, plus, and so on and so forth, right? So, this derivative, because I took the derivative of my original function that I knew how it worked, I took the derivative of the left side, I took the term-by-term derivative over here, and this is the series I got. Okay, interesting. So this then would be our power series for, this would be our power series for this function, simply by knowing that the derivative of this one gave us the function I'm looking for, so I took the derivative of all of my terms. Okay? Cool. If it helps, if we want to write this out in summation notation, we could think about having that derivative of 1, which is 0 there, and then we would get this sum from n equals 0 to infinity of n x to the n minus 1, which you should be able to check when n is 0, 0 times that'll make it 0, right? That's my first term. When I plug in 1, I get 1 times x to the 1 minus 1. That'll give me 1, and so on and so forth. So there we go. That is my power series for that. The radius of convergence, you can probably imagine looking at this here, right? I need, okay, what's going to take x to some power? I need to converge. I'm still going to need the absolute value of x has to be less than 1. I need this thing to be between -1 and 1 if I'm going to multiply by it over and over again to make it smaller. All right? Hold on to that thought. I know this is a lot of examples today. All right. Let's do another one. Given, okay, so this one I'm just kind of giving us right now. I guess we actually did this one earlier, didn't we? We saw that it's kind of this alternating thing, right? So we now know this on this interval -1 to 1. Let's find a power series to represent the natural log of 1 plus x. You might go, okay, well, where is that coming from? 1 over 1 plus x, natural log of 1 plus x. You might be able to go, this looks like an integral kind of thing, an integration kind of thing. Uh, and you're right. We know that the antiderivative of 1 over 1 plus x is the natural log of absolute value of x, right? We know that. And if we're dealing with, say, positive x's, we are going to deal, sorry, if we're dealing with positive argument here, then we don't have to worry about the absolute value bar. And we know that x in our things is between -1 and 1, so this argument's always going to stay positive, so I'm not going to worry about the absolute value bars. Basically, what I get is this then. I know that 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed plus x to the 4th, so on and so forth, right? Which we already saw what it comes out to be, which is basically -1 to the n, x to the n, which will combine as -x to the n, right? If I'm looking at this and say I want to get to this guy, let me take the integral then. We take the integral. I want to take the integral then of everything from, let's do it like this actually. Let's say that we're going to take the integral of, just to not get confused with the with variables here, let's say we're going to take the integral from 0 to x. I'm going to choose 0 because that's where this power series is centered at. 0 to x of 1 over 1 plus t dt. But really all that is taking the integral of this, right, from 0 to x. So what does that give us? This is going to give us then what I know to be the natural log of the absolute value of, we're not using the absolute value, right, because the argument's always staying positive. Natural log of 1 plus t, evaluated from 0 to x. So I'm taking care of integrating this side right now, just this part, to get this, which I now know when I look at this real quick is going to be equal to, when I plug in x, natural log of 1 plus x minus the natural log when I plug in 0. When I plug in 0, I get natural log of 1, which is 0. So there we go, natural log of 1 plus x. That's what I wanted to get to. Equals. All right, now I need to do probably the same thing over here, right? I need to do the antiderivative, the integral from 0 to x over there. All right, so the antiderivative of 1 is going to be x. The antiderivative of x will be x squared over 2, right? I want to actually back this up for a second. Let's use these also just for the sake of keeping things aligned. You know how over here I did my integral in terms of t? Let me call these things in terms of t2 because I'm taking the antiderivative of the integral, and then we'll go back and do from 0 to x. So I'm going to back up and actually rewrite this as the integral from 0 to t of this whole thing up here. Sorry, gosh darn, I keep writing the wrong thing. Sorry, y'all. 0 to x of 1 minus t plus t squared minus t cubed and so on dt, right? Which I know is equal to, when I take the antiderivative, that would be t minus t squared over 2 plus, I got my signs wrong, didn't I? 1 minus x plus x squared, sorry y'all, minus t cubed. 1 minus t plus t squared minus t cubed. Taking the antiderivative of 1 gives me t. Antiderivative of t gives me t squared over 2 plus antiderivative of t squared gives me t cubed over 3 minus, and so on and so forth. I'm going to evaluate this from 0 to x, which gives me x minus x squared over 2 plus x cubed over 3, and so on. So what did I just figure out then? My natural log of x, the natural log of 1 plus x appeared. I took the integral of that side. I took the integral of this side, and I got all this stuff. So let's put those things together. I now know the natural log of 1 plus x, that's supposed to be 1 plus x, equals x minus x squared over 2 plus x cubed over 3 minus x cubed over 4. If I continue, and it's going to keep alternating. X to the 4th over 4. I guess technically over here, then this should have been a minus sign also. Plus, and so on and so forth, which we could then write out as some series from n equals 0 to infinity of -1, because it's got to alternate to the n, x to the n plus 1 over n plus 1. That makes sense because we did the antiderivative. We're going to add 1 to the exponent, then divide by that new exponent. We should be able to check this. When n is 0, that gives us positive. That'll give us x to the first power divided by 1. Yeah, so this series checks out. So now we know that this natural log of 1 plus x is really equal to this power series I have over here. Sorry about my fumbling around there, but here's the whole point. We took the antiderivative of the left side. We took the antiderivative of the right side of what we started with up here as our base knowledge. And we got a new power series. And we can imagine then, okay, if this is going to converge, the ends are going to keep counting. This x over here, we still want to have the absolute value of x to be less than 1 to make this power series converge. Okay? Now, a few observations, some of which, or most of which we actually won't really deal with today. But here's the thing. if we perform, that's called term-by-term differentiation or term-by-term anti-differentiation. We did them both. If we do term-by-term differentiation or anti-differentiation, term-by-term differentiation or integration on some series, f of x, which has some power series, this would be a power series centered at a, and the series looks like this. And we know that that series converges for some value, x, absolute value of x minus a. In this case, a was 0 for ours, so it's just absolute value of x was less than 1. Then the resulting series represents the derivative or the integral of that. So if we do term-by-term differentiation or integration of this power series, we essentially get the derivative or the integral of that function, and it converges like the original series. Now we're not going to talk much about this today because some funky things can happen at the boundaries of that interval. But the interval of the original series and then the derivative or the integral series are going to be the same. It'll converge like that on the same interval. All right. A lot of thoughts we're introducing today. Stick with it. All right. So let's talk about this idea of Taylor series now, because it would be really annoying to have to come up with some variation of 1 over 1 minus x to determine a power series for any function we want. Fortunately, this is where our Taylor series come to the rescue. All right. Ooh, I should capitalize it. It is named after a mathematician last name Taylor, but like many things in math, not actually the guy who invented or discovered it first. The idea of it had actually been around for several hundred years before it got to him. There's at least an astronomer in India who had worked with him at some point about 250 or so years before he did. And I actually should remember this guy's name because it's quite impressive. Give me a second. I think I have it here. Yes, the mathematician's name was Madhava, who lived from 1340 to 1425, and did some of this work well before Taylor did. What is a Taylor series? Well, let's say that f is a function with derivatives of all orders. That means we can just keep taking the derivative on some open interval containing a. The Taylor series that is generated by the function at x equals a follows this pattern. F of a, so the function at a, plus the derivative at a times x minus a, plus the second derivative at a divided by 2 factorial times the quantity x minus a squared, and so on and so forth, on and on and on forever. Essentially, we get plus f to the derivative of a over that numbered derivative factorial, x minus a, to that term number that we're in. Notice second derivative, 2 factorial, second power there. The partial sum, so if we don't do it to infinity, the series would go into infinity. The partial sum of these things, so it's called the Taylor polynomial of order n for the function at x equals a. When a Taylor series is centered at x equals 0, which we often do, it is called a Maclaurin series. Again, the mathematician Maclaurin did not invent this kind of thing, but Hava actually did work with Maclaurin series and things like sine and cosines before he did. But we call them Maclaurin series or Maclaurin polynomials, respectively. All right, let's take a look at this and play around with this some. Let's construct the 7th order Taylor polynomial for sine of x at x equals 0. Essentially, this is actually what Madhava was doing with his work as well. All right, 7th order Taylor polynomial. So 7th order, if I think for a second, back up there actually. Let's go back up. 7th order, the order in here. So 7th order would be, I want to go to the 0, 1, 2, 3, the 7th derivative, which means 8 terms, because the first term here doesn't have a derivative. What does this look like then? Now, writing these out with a lot of orders by hand is a bit of a pain, but there's some ways to organize it. Okay, we want it for sine of x. I know in my Taylor series sort of formula that I want to keep in mind, I'm really shooting for something in the end. I need to have a bunch of terms that look like, I'll just write out the kind of the end sum here. N equals 0, or we'll call it k equals 0, because I think that's what I use. K equals 0. F, the kth derivative of f at a over k factorial times x minus a to the k. I need all of those terms. But I want to start with my very first non-derivative term. All right, I need to start with f, in this case f of x, if I think about it. That should be f of x is sine of x. All right, so I can think about this. I need f of 0 to start with. I like to just write these things out to get the right values I have. F of 0, that's the sine of 0, right? The sine of 0, which is 0. Okay. Then I need the first derivative. I need f prime of 0. All right. What's the derivative of sine of x? It is cosine of x. So now I need cosine of 0, which I know is 1. All right, then take the derivative. I need the second derivative. I need f double prime of 0. The derivative of cosine is negative sine of 0. That's 0, right? All right, and we continue. F triple prime of 0, that should be triple prime of 0, equals the derivative of negative sine will give me negative cosine of 0, which will give me negative 1, right? All right, I need the fourth derivative at 0. The derivative of negative cosine is going to take me back to positive sine of 0, so it's going to take me to 0. Okay, you start seeing the pattern now. The fifth derivative, all right, the fifth derivative is going to give me a value of, I'm back to the top here, value of 1. My sixth derivative is going to give me a value of 0 again. My seventh derivative at 0 is going to give me a value of negative 1. So I should have 1, 2, 3, 4, 5, 6, 7, 8 terms I'm working with. The seventh Taylor polynomial has the initial term plus 7 derivatives. Oh, I'm not sure why I wrote 2 little primes there. That should be a seventh derivative. Okay, now I got to put all this stuff together now. Here's what I need. Remember, I need the derivatives. I need to divide them by whatever term I'm on factorial, x minus a to the term. And I know in this case, a equals 0. So what's my Taylor polynomial going to look like? What do I know? I know then that the sine of x, which is what I'm trying to come up with a polynomial to approximate, this polynomial, is going to be roughly equal to, all right, it's going to be roughly equal to, because this is not going to be exact, roughly equal to, let's do it. The first thing I do is include f of 0. I start with whatever this term is, because k factorial, this is the 0th term. 0 factorial is 1. X minus a to the 0 is going to be 1, so it'll just start off with whatever f of 0 is. There we go. Plus, I need the first derivative, which is right there. First derivative at 0, which is 1 over 1 factorial, times x minus a. So in this case, it's just x to the first power. Then I would say plus. Then I repeat the process at the second derivative level. I take the derivative, I divide it by the term I'm on factorial, and then I take x minus a, so it's x minus 0, which is just x squared, plus, I continue. I would get, in this case, negative 1 over 3 factorial, right? And then x cubed, plus, I'm back at the 0 now. I'd have 0 over 4 factorial x to the 4th. Again, the derivative at that term, I'm kind of counting down my list over here. The derivative at that term divided by the term, or the derivative, factorial x to that power. Okay, keep going. It's going to be plus 1 over 5 factorial x to the 5th plus 0 over 6 factorial x to the 6th plus negative 1 over 7 factorial x to the 7th. We got a lot of zeros in there. We clean this up. So what does this look like? 1 divided by 1 factorial. 1 factorial is 1 times, well, it's just 1. So that's x. We'll lose all of our 0 terms, so this becomes minus, let's see, this minus 1, that'll be x cubed over x factorial. Oh, x factorial over 3 factorial plus, interesting, we lose that one, but we get this one, x to the 5th over 5 factorial. We lose that one, and we get minus x to the 7th over 7 factorial. This is our 7th order Taylor polynomial for sine centered at x equals 0, okay? There's a lot of terms canceled out, but that is our Taylor polynomial 7th term because it goes up to the 7th power. Remember from the video, these factorials come from the fact that we're essentially repeating the power rule and dividing by. So remember, if we undo the power rule, we divide by the exponent. Basically, we'd be undoing the power rule a bunch of times when we would take antiderivatives. You can rewatch the video to understand a little more why these factorials down here show up. All right, but there's the 7th degree Taylor polynomial approximation for sine of x. And we could plug in an x value here that would approximate the sine value of x. We don't know the radius of convergence, so we don't know how close we need to be to 0 to make that good. But a little hint, a little sort of cool thing about sine. Sine, it turns out, has a huge radius of convergence. Here's the sine graph in black, and you'll see the nth degree Taylor polynomial wrap itself around it. 1st degree, 2nd degree, 3rd degree, 4th degree. And notice as we add terms to that polynomial, that Taylor polynomial, our Taylor polynomial actually hugs the sine curve better and better and better and better. This is a really great example of like how a Taylor polynomial converges to some function. It can be really good for approximating that function. In this case, to me, it's like kind of mind-blowing how awesome a polynomial can hug a cosine or sine curve like this. Not all Taylor polynomials converge like this so neatly across a huge interval. Sometimes it's only on a small interval, in which case the curve might only hug your polynomial might only hug your curve in a small section near 0 or something like that. I explained that in the video too. All right, we're almost there. I would like you to do one practice problem here. Go ahead and pause the video. We'll do it and then look at one last example. All right, let's look at and construct the 4th order Taylor polynomial for e to the x at x equals 2. So this is not a Maclaurin series. The last one was a Maclaurin series because that was centered at x equals 0. This one is at x equals 2. So it's just a sort of standard Taylor polynomial. We still will follow the same kind of pattern. The thing we're going to look at is k equals 0 to infinity of f, the kth derivative there at a over k factorial times x minus a to the k. In this case, we're looking at an a value of 2. We still need to come up with all of these derivatives at a. And we're going to start with f of 2. We know that f, in this case, our function, is e to the x. All right, so f of 2 would give us e squared. Great. We need the derivative of f at 2. Well, what's the derivative of e to the x? It's just e to the x. So this derivative at 2 is going to be e squared. The second derivative of that, the first derivative of e to the x was e to the x. The derivative of that was e to the x. In fact, all the derivatives are e to the x. So we need the second derivative at 2, which will give us e to the x, which is e squared. The third derivative here, oh, my f got a little funky looking. The third derivative at 2 is still going to be e to the x, so it's going to be e squared. And then I need a 4th degree Taylor polynomial, so I'm going to take the 4th derivative, which will be e squared as well. We can now start piecing it together into, okay, what does this mean then? That e to the x is approximating. E to the x is approximately then. I follow my pattern. Remember, take my term, divide it by the term number factorial, multiply by x minus a to the term number. This first one would be e squared. Oh, something happened with my pen. Okay. it is e squared over, it'd be 0 factorial. Fun thing about 0 factorial, 0 factorial is 1. So e squared over 1, that coefficient, this thing will always just live there, times x minus a. So this is x minus 2 to the 0 power. If I write out this whole thing, I end up with this. We'll simplify that in a second. There's my 0th term, plus my next one would be e squared. Right, that's the derivative, first derivative there, over 1 factorial times x minus 2 to the 1, plus e squared over 2 factorial times x minus 2 squared, plus the derivative, the third derivative divided by 3 factorial, x minus 2 cubed, plus the fourth derivative over 4 factorial, x minus 2 to the fourth. All right, there is my 4th degree Taylor polynomial then for this function. Let me clean this up. E squared over 0 factorial. 0 factorial, I already told you, is 1. X minus 2 to the 0, that's 1. So e to the x then is approximately, that's 1, is approximately e squared plus e squared over 1 factorial. That gives us e squared x minus 2 to the first power. So I'll just leave it like that. Plus e squared over 2 factorial x minus 2 squared, plus e squared over 3 factorial x minus 2 cubed, plus e squared over 4 factorial x minus 2 to the fourth. So this then is my 4th order Taylor polynomial for e to the x centered at x equals 2. Let me double check my notes, make sure I didn't lose anything in there. All right, cool. And you can notice the pattern there as well. So this is our 4th order Taylor polynomial for e to the x at x equals 2. An important little note, our e to the x Maclaurin series, so centered at x equals 0, if you imagine zeros popping in here for a bunch of things, becomes really kind of simple. E to 0 is 1, plus e to the 0 times x minus 0 is x, plus e to the 0 over 2 factorial times x minus 0 gives us x squared over 2 factorial, and so on and so forth. This is one that you'll need to memorize. We'll talk about that in a minute. All right, and one last example. Okay. The task here is we want to find a Maclaurin series to represent this. This looks a whole lot more complicated, but now that we have all these tools, we can actually just kind of manipulate some functions that we know. If we already know some series, we actually don't have to waste time with stuff. So I want to get this, a Maclaurin series for this right here, right? But I already know a few things. I know, for example, that e to the x, its Maclaurin series is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, right, and so on and so forth. We can just call it x to the n over n factorial. All right, let's start manipulating both sides of this to get something that looks like this. So let's just go ahead and say, hey, well, it's e to the 2x, so I'll multiply that by 2. So I want to come in here and just say 1 plus 2x plus 2x squared over 2 factorial. Because if I'm just manipulating this x thing, that is boom, 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 all those. So if I'm making it 2x, it'll just replace all those things with 2x. That's not too bad. 2x cubed over 3 factorial plus, which gives us 2x to the n over n factorial. All right. Cool, so we can now do our next thing, what do we want to do? Let's say we want to subtract 1 because we want it to be e to the 2x minus 1 and then everything divided by 4. That's fine. Let's do then e to the 2x. I'm going to subtract 1. Well, what do I do if I subtract 1 over here? I want to lose this thing. So really, minus 1 on both sides basically is what I'm doing. I'll lose that one. And I get 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial plus and so on plus 2x to the n over n factorial, right? Basically, I just shifted it back by losing that 1. Okay, so what next? I need to divide everything now here by 4. Interesting. So if I'm dividing this thing by 4, I'm basically going to divide, if I'm dividing this thing by 4, I'm basically going to divide everything here by 4. So what if we said this? E to the 2x minus 1 divided by 4. Ooh, that divided bar got really gross looking. E to the 2x divided by 4. Let's go ahead and call that, let's just say we're going to multiply this whole thing over here by 1/4 then. 2x plus 2x squared over 2 factorial plus 2x. Wow, my guys are trying to look funny. That should be a 2x squared over 2 factorial plus 2x cubed over 3 factorial plus and so on and so forth 2x to the n over n factorial. All right, that's kind of a funny way to look at that, to have like a factor distributed out in front. So let's just clean this up and just call this, let me multiply 1/4 into everything basically, and we would get, I'm going to multiply 1/4 into there. I get 2 divided by 1/4, so that's actually going to give me half x plus 2x squared over 4 multiplied in here, so it's 4 times 2 factorial plus 2x cubed over 4 multiplied in 4 times 3 factorial plus so on plus 2x to the n over 4 times n factorial. And there we go. That would be my my Taylor series, or sorry, my Maclaurin series, since it's centered at x equals 0, my Maclaurin series for e to the 2x minus 1 over 4. I could do some rearranging here. I could call this like 2 to the n times x to the n or something like that if I wanted to, and sometimes you'll see people actually prefer that, to just get the x thing by itself, to call this thing like, oh, not, I shouldn't say equals, because that'd be kind of incorrect. Let's just say that, let me do an error here. That this thing is actually, if you wanted to, equal to 2 to the n times x to the n over 4 times n factorial, if you wanted to write it out that way. All right. Cool. This is sort of the overview of Taylor and Maclaurin series, just to get sort of our feet wet for now. What I'd like you to do is this. On the next page, you'll see the important Maclaurin series to memorize. Kind of everything we will manipulate revolves around these. Several of them we've actually already seen today, okay? These you do need to memorize. You need to get them in your head, in particular like these two. The summation notation is less important, but 1 over 1 minus x is equal to this, e to the x is equal to that, sine of x is equal to that. Those things are important to memorize, okay? So if you'll get those in your head. The homework today is relatively short because I knew this video would be kind of long. In the homework, you need to do textbook problems page 500, numbers 1 through 4, 5, 13, and 19. There's no check-in quiz today. All you need to do is make sure you practice this, and I'll put some extra help online. And you can, if you want to, start looking at the concepts also. I want us to take our time with this, to really digest it, not overwhelm you. Thank you for your time. Make sure you take a look at all my announcements and things, and I'll see you next time as we start wrapping up this year. Okay? Bye.